Okay. This is like a presentation, but I very much welcome the breakout of a discussion at any time. I think that's how this could be most interesting. On the topic of all the introductions and just I have some thoughts building up from having had to be quiet for so long. One would be like definitely if you're thinking of presenting at this meetup, there's not an expectation that you won the competition that you're participating in, or that you did well, or that you even participated. We've had a number of good presentations from people who did not participate even in a competition. And sometimes I think just to facilitate a group discussion on these topics is worthwhile. And so don't be like too intimidated. And then like another comment, I hear people talking about their backgrounds and so on. Like a little bit about me in that sense, like I had an undergrad in math, and then I studied actually a precursor to that MBAN, I think. So I did a Master of Management in Operations Research in the Sauder School of Business at UBC, which is not like the kind of master's degree that would naturally lead someone to present machine learning. Well, actually you might present because that's the kind of thing they focus on, but to do machine learning, but that like, so philosophically, like your career is not like strictly dictated in like a one foot in front of the other. And I say this because I know probably there's a number of people in the audience today who are thinking about taking their career in a more technical direction. That's part of why they're here. And I would say like my membership in this community has been a part of that journey. I think you have to be somewhat mathematically strong, and with an undergrad in math, like I can claim to always have been, but it's a pivot, and it takes energy in a lot of forms. I think attending these events is going to be a great, just sort of like lecture kind of classroom style to learn some things. I think participating in these competitions to do anything is worthwhile. I think if you copy and paste like a script that somebody has provided and run it, like you're not going to learn a lot. But if you can manage to get yourself infected about like, well, what if I tried this and what if I tried that, and you have to start coding it up, you can get a lot of valuable experience for the workplace, like in your own time, which has its ups and downs. You need to love it, that's for sure. So that's a little bit of background and some thoughts. I'm here to present this Isaac 2018 Skin Lesion Classification Challenge, and we won, so that's great. My teammates, Jordan and Will, can't be here, but I need to put their names up there because they were in a big part of the fact that we won. And we all work for Optima, which as a company I'll talk about in a moment. Isaac is some kind of, and I don't know the details because I'm solving the math problems, but some kind of international skin something organization. They put on, like, I'm being recorded, showing that I don't know, and acting like I don't care. They put on an annual competition. So this is the 2018, there was a 2017, there was a 2016. These competitions have been a big part of pushing the envelope of what can be done in this problem space. And then finally on this slide, I would say, so if you work in this space, sometimes there are images that are a little kind of disturbing, but if you're not disturbed by this slide, then you're going to be fine in this presentation. This is like an embedding, by the way, if you might notice that the dark moles are together and the light moles are somewhere else. That's kind of cool, right? Okay, so shameless plug / kind of interesting explanation. So Jordan, Will, and I, we all work for Optima. I'm a machine learning engineer there, so are they. Optima is a local Vancouver company, about 5 years old. We're doing digital health and skin is what we're very interested in. We have like two principal offerings, and they go together. So we have a mole scope. It's like a macro lens attachment for a smartphone, which would allow you to take exactly the kinds of images that are in this competition. That we call them dermoscopic images, rather. So it's derm, skin, and scopic as in like we have a scope. And then along with that, we have this very important platform. Well, I probably don't use the word platform, but Derm Engine is this associated software for people to manage their moles, manage their skin cancer risk, deal with these images. And so like this is what this competition is about is like therefore like a natural place for us to be working and a natural ambition for us. I'll also take an opportunity on this slide to say, we're a growing startup, we have some funding, and so we're hiring. We don't have like precise job descriptions because a company like ours doesn't, but we're definitely looking for bright machine learners to join our R&D team. And then the job title that people throw around is sort of a data engineer. So if you're a competent, like software engineer who like knows data pipelines and databases and so on, but you're interested in machine learning, we absolutely could use that kind of support in our team. Right, so this challenge is actually 3 tasks. And I thought I'd just mention these here because they're kind of interesting. They're all related tasks in this domain. So the first one here is this this lesion segmentation. So by the way, there's a few words that like I might just use interchangeably here. Lesion, mole, spot. I mean, for our purposes today, they're all basically the same thing. These are the dark freckles that are on your body. So one is this segmentation task. If you're familiar with these Kaggle competitions, you've seen like something like this before. You know, you're given an image like the ones on the left, and you're expected to output something on the right, you know, a bit that's 1 or 0 for each pixel in the image to tell you whether or not this is a lesion. There are lots of reasons you want to do this, and I don't think we need to get into that. Task 2 was this sort of lesion attribute detection, which is actually kind of a very interesting problem. So somebody has essentially, I mean, they've labeled these images to say that certain properties are present in certain places. And why that's interesting, of course, is that's how a human diagnoses these things. Like if you look at a lesion and you want to know whether you think it's a problem, is it skin cancer or something like that, I mean, you're looking for these properties. And so, so that in itself is an interesting task. But today we're here to talk about disease classification. And so, like again, there are multiple tasks, but we're only going to focus on this one. Here it is in greater detail. So this is like a 7-class classification task. So you're given an image that looks like one of these, and you're expected to output probabilities for these 7 classes. These are by no means all the classes in the universe, and that's kind of an important simplification. They're most of the important ones, but not all of the important ones. And so, you know, we are in a simplified sandbox here, obviously. Why would I want to be able to do this kind of thing? So what's the motivation here? I mean, obviously, there's this idea that, you know, doctors who are doing this work today are expensive and we can put them out of work with artificial intelligence. I mean, obviously, like, that's the soundbite but it's yes. I can repeat your question if it's short, or we can.
Yeah, there's no null category?
Right, no. So yeah, so on the technical topic there, in the test set, so the question, I won't repeat the question, I'll just answer the question. Every image is one of and exactly one of these 7 classes. And so there's no possibility that it's some other, and there's no possibility that it's 2. These are mutually exclusive, collectively exhaustive for our purposes. Oh, sure, okay.
In actual skin photos, though, is there a possibility of there being 2?
So it would depend on how you've decided to break down the world. So, like, but yes, but I mean, you can come up with a taxonomy of the world that has very little of that if you want to. Okay. These 7 would always be mutually exclusive in any setting. Probably we're not about to put a whole bunch of doctors out of their job by writing a machine that does this sort of work that they do today. But we certainly can augment them. There's a lot of associated problems here. I think when a doctor sees one of these and makes some judgment, they're doing a bunch of probabilistic reasoning, right? Like they don't say, oh, it's definitely melanoma. They say, oh, it's like it's a chance that it's melanoma. Is it a high chance or a low chance? Well, even if it is a low chance, like how do I feel about low chances when it's something with high consequences? And then there are risk factors and so on. There's a lot of complexity there that I think we can support a doctor with without question. And so it's a very interesting topic. We also have like a lot of underserved people in the world who don't have access to doctors or aren't anywhere near a doctor, including places like Canada, Australia. You'll need a microphone, but.
Yeah, sorry, I was just about to say that. The same thing, there are so many places in the world who... There are so many places in the world, I've been in one of them, who would have, like, having a machine learning algorithm is actually more important than having a doctor because these things are... in some places of the world, they are not really abundant, so doctors don't really know. Actually, real doctors cannot really differentiate, and there's lots of misdiagnosis. I've been working in the cancer field for 5 years now, and I've seen so many patients go undiagnosed because of doctors who are incapable to differentiate between dermatofibroma and melanoma. And this is a big problem. Maybe if you're not a doctor or if you're not from a medical background, you would think this is impossible, but this is really highly possible for many doctors, oncologists who would not be able to differentiate these. So maybe in Canada, it's highly unlikely, but 80% of the countries in the world, their doctors might not be able to differentiate them.
And there's a lot of people who aren't going to see their doctor, and if they could self-serve themselves with a smartphone, things would be different, even in Canada.
I'm guessing this is probably going to come out shortly, but I'm curious. So all the photos look like that's on people with fairly pale skin. Do you have other photos with different skin tones, and is it harder on, say, darker skin tones versus lighter skin tones? I see some little pinks that come through that I don't know how well they come through on various skin tones or not.
Right, so this is actually like a broad problem in the field that like the vast majority of research is done on Caucasians, and the vast majority of the data sets are on Caucasians, and by no means do everyone who dies of skin cancer on Earth Caucasian. And so this data set will be entirely pink skin, and a machine learning model trained on this will not be transferable to other skin colors. I can say that with confidence. And so that's a big issue, like at a systemic level for sure. Right. Those are the main issues here. So every competition pretty much has a data set that usually would be a data set that they provide for you to train your models with, and then also a data set that you're expected to make predictions for, essentially the test set. In this competition, you're actually permitted to use external data, but they still provided a data set, because if they didn't, no one would participate. That's the way these things work. And so the data for this was this Ham 10,000 data set, which is really like an amazing data set. So on the slide here, it's just meant to illustrate it a little bit. There was data from like many sources, photos in PowerPoint presentations, like physical slides that used to be like photos or whatever, and like actual like images and directories and giant piles of directories. And it went through like a very extensive and rigorous cleaning and sort of normalization process. So like not every photo is reasonably centered. Some of them are terribly taken. Some of them have white balance issues where they're kind of completely out of whack or too dark. And there's also like a big challenge with labels in this space. So what is the diagnosis really for this lesion? You often would get like conflicts between doctors because they're not perfect at this. You also sometimes get sort of varying diagnoses where like at first it's judged to be like possibly problematic, but we're not sure. And then we cut it out and look it under a microscope, and then we know for sure what it is, although even then you get debates. I'll point out that the quality of the diagnosis in this data set is really high. The imagery is really high. It's amazing for this community. The amount of images available to work on these sort of problems is more than doubled as a consequence of this. And if you want the QR code, I guess. Okay, so we're going to get, oh yes.
Hey, sorry. So are all of those images of the same size?
I believe it varied.
Okay.
Yeah. We made them all the same size. Yeah. So we have a competition metric, which we're talking about, and we'll talk about it more later. Like a normal competition for making classifications would have something like accuracy, although that's pretty crude. And so we like to have these negative log loss cross entropy type metrics, or area under the curve, whatever. The metric for this competition doesn't have a great name. I don't have one I love. But we might call it mean recall. And on this slide, I'm illustrating the key difference here. So on the left is the kind of output you'd get if you use the sklearn confusion matrix method. So this is a visualization of a confusion matrix. Essentially on the y-axis is the true class, I believe, but you could draw it differently. And on the x-axis is the predicted class. And so, if you had a perfect classifier, all of your predictions would fall on the diagonal, but some of these are easily confused. And if we judged your accuracy from this, the fact is that this data set is highly imbalanced. Highly imbalanced. There's a huge number of NV, Nevis. And so it has a disproportionate weight on your accuracy score. And if you had an algorithm that knew nothing and all it just said was Nevis, 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 like it would score 80% or something. I don't know the actual number. And so instead, for this competition, they used this mean recall. And so to visualize that, on the right, I have more like what you might get. This method call here, sklearn metrics recall score, with an average macro. Don't ask me why they use these words. If you use that function, you would get the right number as a result. Essentially, what we do is we normalize each class by how many items there are in that class. And so essentially, we end up with a per class accuracy, or recall in this case. So this VASC at the top, like what percentage of those did you, that were truly VASC, did you output VASC? And then we can take an average across the classes. And so this is a much more balanced way of measuring your performance. You don't get easy points for just predicting the majority class all the time, and you need to be able to get those harder examples all equally. One of the Alexis.
Yeah. So my question, why wouldn't they provide negative examples, having spots that are not cancer? Because my guess would be that most of the people are concerned about if they have a spot and they are not able to receive the professional help, they would be concerned about if they have cancer or not. They don't really care about what type of cancer at this point, right? So having some negative examples, I think would be interesting.
So Nevis is essentially a negative example, which is this sort of predominant class. But there are some interesting points in here. So Nevis is considered not a big deal, and that's the dominant case here. But to have come into this data set, you have to have been suspicious, essentially, because you ended up seeing a doctor and you ended up having these photos taken. And boring, totally safe moles don't ever have that happen to them. And so you're right that what is the real problem and where did all this data come from? Those are also interesting issues. And you'd have to be very careful with how you wanted to use something like this. The other thing you touched on too, in practice. So this is a competition with a competition metric, right? And here it is, and it's cold and hard, and it's that way. But if you're going to use this in practice, you need to reflect on, what is the decision that we're making here, right? And indeed, I think the primary decision in this case is, do we cut it out or do we not, right? And I think, and I'm not an expert in the domain, but then the key trade-off here is if you're cutting things off of people who don't need it, that has a cost both physically and economically. But if you let things go that turn into a problem and kill someone, that also has a cost. And so there's a balance you're trying to make there. And if the model or the human, either of them say 5% melanoma, that, and 95% totally okay, you might cut it out. Right? It's not like 51-49 is the split. And so that's a big topic and oversimplified for the purposes of a competition, right? And so here we go. And now each class is essentially equally important, and I welcome this. We can do this all night.
So that was what I was just going to ask, actually. Does that mean recall mean that you're essentially weighting a wrong answer for one of the minority classes more heavily than a wrong answer for one of the majority ones?
Essentially, yes. And that's really important. We'll get into that for sure. Here's just a look at the leaderboard. So you can make 3 submissions, which is why we came first, second, and third, but obviously we just came first. I mean, once you have a good solution, making new similar submissions is not that hard. I just put it up to show that so for one, yes, we used external data, which is what this little orange thing indicates. So did the second place team. But I mean, the third place or fifth place, however you want to say it, did not. And so they did quite well considering. We'll touch on that in a moment. I point out that we actually had a pretty healthy gap between our first and second. And I guess we had teams from all over, for sure. That's what I'd point out here. Right. So in this presentation, I'm going to try and include things for newer people and things for more experienced people. I'm going to breeze over this like really quickly, but if people start asking questions and we want to go into it more, like I'm totally okay with that. You can see I didn't do much to make this slide, and I didn't steal a slide from somewhere else. Like a thought when we began working on this competition is like nobody is going to invent a brand new image classification technique to win this competition. This is like such a well-researched field. People doing it all the time. So probably we'll be using established methods. And like I boldly stay here. This is the only way to solve this problem is in the following way. So ImageNet is this famous data set. Essentially, it's 1 million images, and there are 1,000 classes, so there are like 1,000 images from each class. And it's this like benchmark competition that people have been working on for years. And what you do, in the way that our data set is sort of 10,000 images from 7 classes, right? And so what you do is you train a convolutional neural network, and we won't even talk about what that means, it's fine. We train a neural network using these images to predict these 1,000 classes. These are photos of like cars and horses and typewriters, and it's a crazy mix. Several different types of dog. And you end up with a neural network that can perform shockingly well at classifying these images. And then you do this fine-tuning step on the pre-trained network, which is basically just more training. So you do exactly the same procedure that was done to create that network, only you change where the data is coming from, and you change what the classes are. So you switch it to, in our case, 7 classes, and you switch it to images of moles rather than photos of parrots, and you do more training. And essentially, if you're going to train from scratch, you would randomly initialize, well, very cleverly randomly these days, like initialize the weights in your neural network, and you'd have to build from there. But if you have this pre-trained neural network, it's already very good at looking at photos of dogs, and now maybe we can leverage that somehow and just change it to look at photos of moles. And you know, there was a time when this wasn't obvious. There was a time when this wasn't obvious when the domains were very close. So we talk about that in this case, where, you know, how different is the new task from the old task? People do shockingly well on really different tasks. I think I consider it like a minor miracle. Like, I mean, I remember the like synthetic aperture radar Kaggle competition for icebergs and ships, and people like, I mean, these are like log scale responses from some satellite hitting like the ocean, and yet people are using these ImageNet weights and gaining benefit from it. So totally different stuff. I mean, these moles are like pretty different. I mean, these aren't dogs, these aren't cars or anything, but it works. And like we knew going in, this was the only thing anybody was going to do. And indeed, well, a couple of people tried training from scratch, but it just doesn't work out. I don't think I have any questions on that, but yes. Oh, no, Bruce does. No, you don't. You have a point to make. You know this stuff really well.
No, you probably said this, but I'm just curious. Did you say how many images you do have that were supplied to you?
Right. So the 10,000 images were made available, and around 1,000 images were in the test set.
Which is not a lot to be training from scratch.
No, definitely not. Yeah, that's not going to work. Basically, period.
How many extra?
So you have to hit the button at the bottom.
How many extra images did you have in your additional data?
I think it's like almost on my next slide. Cool. Yeah, I'll cover that like with the slide up. And then the other comment. This is the how to maximize your score with ensembling. And so briefly about ensembling. So here you can see what I did in the slide here. I took my previous slide, but then I kind of made it in the background to say do many times. And so now I have like what would have been a query image that I would have given to one model that I did one time, and it would give me one set of outputs. And I could do that many times. And then if I do some kind of ensembling function on these many predictions, I can generate a prediction that's better. And some of the low-hanging fruit here is like shockingly easy to collect. Like there's a lot of randomness in this training process. And if especially, I mean, so you train on these mini batches, and just the ordering of those and so on will deliver you a different result every time. So if you just put your training thing in a loop and you just do it 5 times instead of 1 time, and then you average their responses, you get gains for free. But you can do better than that. So you can take 4/5 of the data and train a network, and then take the other 4/5 and the other 4/5 and the other 4/5, and now you have 5 that have seen slightly different versions of the data. If you average their responses, you get a better answer. There's a whole world of complexity in the ensembling. We need to get that person a microphone. Is there one in the deep back there too? There is one in the deep. Okay, here, it's a race.
Okay. Hi. Yeah. So I know one method to increase the sample size by like rotating the image you have. So like I think it's a good way because then you know like if we rotate like the same image, it's still like that cancer, but we can like analyze it from a different way because the convolutional neural network, the filter is like moving horizontally or vertically. It's not like rotation can really help us to better understand the images. I just want to know like, did you use this like method or not? Like
I have a whole slide about data augmentation, and I'll cover that and other things just a little bit later on. But it's worth commenting now that, I mean, so any one training run has a number of decisions that go into it, and everything is a hyperparameter, he said, pointing at Matt, right? And so every one of those decisions is a lever that can be changed in order to get a better result. And often we just do it empirically and figure out what works. But those are also things that you could deliberately do differently in order to end up with different models for your ensemble, right? And so you might change your data augmentation procedure for one model from another. And if you average their results, you might just magically get better results. Averaging is the simplest thing to do, and it works shockingly well. But you might instead have a score for how each model performed, and then do like a weighted average based on which models were better, and so on. You could go down the rabbit hole, but this is like free improvements almost. They only cost coding and electricity.
I have a really good question that comes from the live stream, not from me. It's actually from Matt Palma. Question, it's about ensembling. Was he ensembling many very similar models or highly varied? For example, ResNet, DenseNet, AlexNet, etc.
I'll talk about our ensembles later, so I'm just going to keep doing this, but I will get to that for sure. Yeah. Okay, so now we'll start getting into this. So why did we win? Why do I think we won? So I said, like, these are the only way to solve this problem. This is the kinds of things that you do to get performance increases, and everybody knows. So I have to put this up here. Can I say that this is why we won or not? I can't really definitively say. I haven't done the experiment. We had proprietary data that we could add to our training data. What I have here to show is, so that ham 10,000 is actually 10,015. If I were them, I would have deleted those 15, but they didn't. There's also, there's like 4,163 images available through this Isaac organization, publicly available, that, I mean, is kind of trivially easy to add here. You can see why I said it more than doubled the kind of imagery available. And we had sort of 30,000 odd extra images available to us. Not everything is exactly the same, though. That's really worth kind of reflecting on, that like the data in this competition came from a diverse set of sources, and as I said earlier, went through a rigorous process to try and make it all kind of similar. But different photos of different patients in different countries, at different clinics, at different times, with different equipment, and so on and so on and so on, will be different. And more data from some place that's different is not necessarily better, or not necessarily a lot better. And so, of course, we have data from a number of sources as well. Here's yes, we'll take that.
I was just wondering, do you know how many additional data points the other team, the second place team that added augmented data
I don't know that, no, sorry. I could probably find out. One element of this competition is you were expected to submit like a few-page manuscript describing what you did, and anyone who placed well certainly was required to do that. So that's, you know, in a typical, going back to, again, encouraging people to present, a typical Kaggle competition has a number of people who do very well, and they like to tell everyone what they did. And so when you're researching to facilitate a presentation, I mean, you can go read what they did and then sort of share that with the audience. And so that was very much available here. Here I just sort of show you the distribution. So this serves two purposes. It shows you kind of how our data differed from the actual data. In terms of class distribution, there's a lot of ways that things can differ. And also gives you a sense of the class imbalance. So this nevus is huge, it's dominant. And then, yeah, this dermatophobona, this DF, is like a tiny, tiny minority class. So there's not a lot to train on. There's not going to be a lot in the test set. And they're going to be really important if you want to maximize your mean recall. And so that's where I get to this. So I'm going to talk about hacking the competition metric. And like whenever the competition metric is not the basic, simple thing, like getting this right is the difference between winners and losers, for sure. And I have tried to explain this to very intelligent people and failed sometimes. So I may fail again here. This is going to be a relatively advanced part of the discussion, but I welcome, like, please try to get it. So I'm going to walk through my argument here. Okay, so the key insight, mean recall is not accuracy, okay? And so what we normally do when we train neural networks is we optimize this negative log loss. And it happens to be that when you optimize negative log loss, you're also optimizing your accuracy. That is, like, of all of the answers I give, what percentage of them are correct, which, of course, doesn't think about the class imbalance. And actually, little note, I read something recently that suggested that as networks are overfitting to the negative log loss, so your validation loss is going up, your accuracy might still improve a little. And it's like, apparently this is an observed phenomenon, and I consider that spooky. And if I were starting a PhD right now, I would be going after that, because it shouldn't be the case. Really, like, optimizing negative log loss should optimize your accuracy, although, like, overfit, like we make a bunch of simplifying assumptions when we make statements about these models, and the fact that we're training on batches that they overfit might ruin some of those things. So yeah, we have highly imbalanced data, so not all mistakes are equal. Yes, Paul.
You're probably going to cover this shortly, but I'm curious. So on the images, there's one class where there's a whole bunch of them. And in training, you can just sample some random amount from each one. So you could just take an equal amount from each class. So you could have still trained it on some other method that looks at accuracy, assuming that you're taking the same amount from each class or otherwise. Did you consider that? And comments or?
Yeah, I have a slide later about what didn't work / didn't matter. And there, yeah, so there are a number of techniques for training with imbalanced data. I'll touch on those in just a moment. It'll fit nicely just like the later end of this argument. Okay, so as was pointed out earlier, like, certain types of mistakes matter a lot more than others when I'm running the test set. If I make a mistake on nevus, it's only like some small part in a giant pile of nevuses. But if I make a mistake on that DF, that tiny minority class, that's going to be worth a lot. And so yeah, that's an important observation. So what are we going to do about that? I have this bullet point here. Normal predictions are tilted by our prior belief. And so here's, like, if our model looked at an image and it thought it was totally inconclusive, it's like, I can't tell from this image at all. It's like a black image, right? What does your model should say? Well, it should say the majority class. It should say nevus, because it knows, like, all things being equal, I mean, that one's the most common, right? And so ultimately, we have priors, really. We have this, like, we have this prior belief as to what the class distribution is. And then when you give me an image, I'm going to update that prior. And so if the image was a 50-50 split between melanoma and nevus, and I know that most of them are nevus, I can say nevus. It's just natural that I would do that. Just human rationality would do that, and so would your model. So should your model, if you want to maximize accuracy. And so I present here without proof. I have a kind of an argument. I would welcome, like, an actual proof. But I would say here that the optimal thing to do when we want to maximize our mean recall is to behave as if you believe the test set is balanced. So when it's 50-50, you don't output nevus. Well, what do you put? We all have to output something. Well, you would put 50-50. And if it were like 49-51 49 nevus 51, sorry, 49 nevus 51 melanoma, right? In the normal case, you would still actually tilt towards nevus because you'd say, oh, I only think based on the image alone, I think there's slightly more evidence towards melanoma, but I know that most of the data set is nevus. And so your model will actually output nevus in that case. But you need to behave as if you believe that the data set is balanced. And so as a thought experiment as to why you should behave that way. So suppose that the test set is balanced, okay? And we're going to behave as if it's balanced. Then that's great. I mean, we did the right thing, right? But suppose the test set isn't balanced. Suppose there are a lot of nevuses, but I'm pretending like there aren't a lot. In this case, I'm going to say nevus less often than I would have. And I'm going to say some minority class more often. And that's kind of exactly the outcome I want. This is not going well, I can see. I can try, so then that was my, not theoretical argument. I have some stuff more based on the math. So if you read a machine learning for developers style introduction, they're probably going to tell you about negative log loss, and they're going to tell you that it has these nice properties, like it penalizes confidence mistakes more than others, and so on. If you read something more academic, they talk about these things called KL divergence and categorical cross entropy stuff. They don't necessarily jump right into the mechanics of it. But this is important though, because these factors mean that your model actually outputs probabilities. When I first started coming to these a couple years ago, I was very much this probability skeptic. And you're like, oh yeah, your model, it outputted numbers between 0 and 1, and they all totaled to 1, so you call them probabilities, but they're just numbers. But actually, they behave like probabilities. And there's a really interesting paper about this, or at least I found it really interesting, about the calibration of modern neural networks. So they looked into this, is it actually a probability? And there are statistical tests and visualizations that you can use to ask, do these things behave the way that a probability should? And they find that mostly they do, although the really big modern convolutional neural networks don't quite behave properly, and they have this really simple procedure for fixing them. So these theoretical things mean that they're probabilities. And your neural network is trained to minimize its expected loss over batches. And therefore, it is going to output the best estimate about probabilities it can for a batch. And if it's doing that, then Bayesian reasoning is the only way to do this. And as I said earlier, you have this prior knowledge about how the classes are distributed, and then you see an image, and then you update that prior knowledge. It's just it's logically required that we would behave that way in order to optimize these things. Therefore, your neural network has a prior. It has a prior that it's learned. As you feed it these mini batches, randomly sampled, maybe, from your training data, it sees this prior distribution that's mostly nevus. And so it has this prior built into it. It has to, otherwise it wouldn't make these optimal choices. And so our network, if we use it just bare bones on the test set, it's going to behave as if it knows nevus is really common, and it's just going to say that if it's unsure. But we can change that. There's a simple mathematical procedure to change the prior of something. So we can change the prior of our neural network to be balanced rather than as per the training data. And we can do it in this way. I've made it look way fancier than it is. And essentially, we create a weight that's the inverse of the class frequency. So the things that are small get a much bigger weight, and the things that are very common get a smaller weight. We multiply that by all our probabilities, and then we renormalize, and it goes back to a nice set of numbers that sums to 1. And again, I would like to be able to prove this. I got most of the way, but there's something I couldn't do. And is that a question in the back? Go ahead, Morgan.
Yeah, thanks.
Sorry, I need that again. Or
Is this a superior method to changing the weights of the neural network?
Right. Okay. So is this superior to changing the weights? And so okay, we've had this twice now, and so I'll go to that topic. So yeah, so there are many ways of addressing class imbalance, and we can see by reading the manuscripts of some of the other competitors that they absolutely tried these things. So one of the things that you can do is essentially oversample your minority class. is what we call it. So instead of like randomly sampling batches from my data kind of equally, I now sort of deliberately try to sample in such a way that my neural network sees balanced batches. And so therefore, it's going to compute its weights. It's going to learn to behave as if the world is balanced. That's the prior we taught it. So we can do that. Alternatively, we also can do weighted losses. So we continue to sample the way we were, but now when we're doing the loss function, we penalize some losses more than others. We might do them with exactly this ratio, and I think there might be some theoretical arguments that say that it works out to be the same result. In my experience here, doing this reweighting afterwards was always better, which is really interesting. Like, it's funny, I was having a debate with somebody about this, and I said that if I can change the prior of my neural network to fix this afterwards, then the real question is, like, does the class imbalance limit my neural network's ability to learn? Like, did it learn less? Because it outputs some numbers, and we can choose to interpret those numbers how we want. We can adjust those numbers. I mean, anyone who's done binary classification knows that we like to pick a threshold, and we can pick a low threshold to pick some kind of balance between precision and recall, or specificity and sensitivity, other way, but anyways. Or we can pick some other, we can do lots of things with the outputs of these models. But the question is its learning limited? And indeed, sometimes the class imbalance is so extreme that the class almost never shows up in a mini batch, and so its back-propagated gradients don't happen very often, and your model just completely fails to recognize those. Go ahead, Kenneth. Maybe that one doesn't work.
It works now, yeah.
Right.
Yeah, I actually like this method, this way of correcting for class imbalance. So I didn't know this before, but now I know it. So now I have one more question. If you were doing segmentation, for instance, and each pixel could be containing the object or not. So how can you correct? So can you apply this to segmentation? This is for normal multi-label class. But can you do something like balancing stuff in segmentations?
Yeah, I think so. I mean, I think when you train that pixel classifier, essentially, right? I mean, it has these prior beliefs about how common certain classes are, and it's going to act accordingly. And if you want it to act differently, then you could apply this procedure on a per pixel basis. It's cheap, right? There's almost no math here. Go ahead. No, you got it.
So my question is about weights. I guess that's like a constant for the training set that you're working on. But do you use that for your loss function, or you actually just apply weights after learning is done, like when you actually do the prediction, right?
Yeah, this is, I do this afterwards. You're right, you could do it in the training. That could be interesting. But yeah, I mean, sorry, I guess maybe I didn't make that clear earlier. This is like an inference time thing. So
no, I understood that from what you were saying. It's just I wanted to confirm that it's after training you apply that, just waiting.
Yeah.
Sorry.
Yeah, go ahead.
Go ahead, and then we'll get it up.
So when you are taking different samples will have different distribution, right? Do you update the prior according to the distribution of the new sample, or do you just assume they have the same distribution?
So I train a neural network without thinking about this at all, in the totally normal way. And then afterwards, you give me an image, I make a prediction, and then I change it. And I adjust it in this way because if I know I change it in that way, I optimize for the competition metric. Yeah.
Hello? Okay, great. Just a quick comment. This is also available through scikit-learn. There's a similar thing in the calibration sub-library in case if you need to do this for not a neural network. My question is, what is S here?
Oh, it's like a score, adjusted score, I guess, basically. So it's the weight times the probabilities, and then renormalized by the sum of those, which seems like crude magic to make it numbers between 0 and 1 that sum to 1, but it's legit, right? And that's part of why I can't prove it. I bet you Andrew could do it.
So the reason you have to sort of jump through these hoops is because the evaluation metric kind of assumes that the classes are balanced in a way. That's by construction. And the reason you're not using the evaluation metric as your loss function is because it's not differentiable directly. But for various things like that, there are sometimes differentiable approximations to the evaluation metric. Did anybody go down that path that you know of?
Most of the reports that I read were exactly this, like oversampling or weighted loss and things like that, which I guess is sort of that, but nothing fancier. But like, so this is like about hacking the competition metric, which thou shalt do, right? Because it matters. But it's like worth reflecting on, like, what do we really want in real life for this? I mean, okay, so we're not putting doctors out of a job, but what are we really doing? At the end of the day, like, we're not giving binary classification. We're not just saying, oh, this is that, this is the other thing. We want to give probabilities, and we want to give like well-calibrated probabilities, right? That are actually meaningful and so on. And so this is all part of the same thing. And yeah, you can take a model that you are suspect about its scores, about whether or not they're probabilities, and scikit-learn has these nice calibration functions in them, and I've used those. You wouldn't want to use them on a neural network, but like I said, that paper has an interesting procedure. Okay, so people, let me just do this one right now, and we'll go to questions because I need to get it off my chest. So people train models on imbalanced data sets, and then they look at the performances, and they're disappointed with performance on the minority classes, and they interpret that to mean that their model hasn't learned. And I think that's that's a chronic issue. I don't think that's the case. I think that what they're seeing is their model's bias towards the predominant classes that it learned from its prior. And I think people have these sampling methods or these weighted losses, and when they try them, they then look naively at the outputs from their model, like, oh, look, the performance on the minority class went up. The network learned more. And I think there's this whole myth that built up around that. And in my experience, all of those things could not outperform training it normally and then fixing its probabilities. Yeah, go ahead. Oh, we're very strict about microphones. I don't know if you noticed. I tried to get away with it on the first one.
Hi. I just wonder, how did you set the first prior here? And is that depending on the imbalanced data set, or is it depends on, like you mentioned, if there's an image and the probability shows it has 50% belongs to A and the 50% belongs to B, and you say by human common sense we know it is A, not B. It's how do you what is the prior about? Is it about data size or the probabilities of the disease?
So I'll say that if you do the normal thing, which we did. When you start with this network with randomly initialized weights, it essentially has no prior right at the start. And you see these sort of dramatic changes in the first few training iterations, basically as it figures this out. The first thing your network's going to figure out is that it should be outputting, by default, the predominant class. It's super easy for it to learn. And so you see that dramatic increase right at the beginning. I think, I've done some math here. I think if you set, this is going to be technical, but you set the bias on the fully connected layer at the end in such a way that it reflects the distribution in your training set, and I can write that down another time. I think that's like giving it the prior that you know from the data. And somebody should get Robin a microphone, because I'm interested in what he wants to ask.
So are you saying that your method of adjusting the probabilities at the end is better than injecting the bias or by changing the sampling method, like the other ways of addressing the imbalance? Do you think it's better? Do you think it's a better way in general, or it happened to work well here?
I think there are probably scenarios where class imbalance limits your network's ability to learn. It's that rare, and your batches are that small, and so it doesn't cause the weights to change. It's like it's never seen anything from that minority class. But at least in this case, with these balances and the networks we were dealing with and so on, we tried many things and nothing outperformed doing things normally and then changing it at the end. And Morgan had a question in the back.
Just a guess for why?
Oh, you're going again. I don't think you're on again.
A guess for why?
Oh, sorry.
Okay. So it feels like regularization will probably work more effectively in the way that you've run this, as opposed to if you artificially sample in an irregular way.
Can you expand on that? Like what kind of regularization specifically?
This could take a while, maybe afterwards.
Yeah, okay. Yeah. Okay, maybe that's okay, no, we'll keep going, good. That works for me. This is my favorite topic. You have a microphone.
I was just wondering whether you had any insights as to why adjusting the priors like this worked in your experience better than adjusting the log loss through a weight.
Yeah, I think, okay, so definitely if you ran a weighted loss, your network has learned a prior still. There's something in there, but now it's a bit mysterious. Like I don't actually know what its prior is. It's obviously it's not quite going to behave like as if everything is Nevis, right? But it's also not probably quite going to behave as if the world is balanced. And so we could probably do a procedure like this, but we wouldn't know what to do. Because I would no longer know what to do this adjustment, I have to know the original prior and my desired prior. And this network that gets trained in the way, I don't know. And I experimented a lot with some sort of numerical techniques, to try and, given a network and a new validation set, try to find a prior that would be best and so on. Because I also wasn't totally certain that this was correct. And so I tried exhaustively numerically to try and find something that would perform better, and I didn't. So that was very nice proof. But yeah, I think that maybe if we could figure out what the adjustment was, maybe those networks learn better, and when we do whatever the right thing is, they perform better. I don't know. Okay, we're going to move on to some sort of more basic, factors that I'd say. Okay, I have this in the why we won section. That's not really fair because lots of people did this. But so this is maybe the why this is a super important thing in this case at least with test time augmentation. So we'll talk about training augmentation in a moment. But basically, in a very simple sentence, we did not simply take an image, give it to our network, and take the prediction. We came up with 24 variants of that image and ran all of them through a network and took its prediction. I have the details here about cropping and resizing and so on. You kind of randomly crop to move it around a little bit. You zoom in, zoom out, and so on. Rotate, like we had earlier. That's an easy one, always a good win. And then demonstrate. So we had lots of models. Here are just some we pulled out. This is the kind of improvement we got. So I'm not using the competition metric here. I think loss is great number to make your decisions based on because I can make adjustments. I can have different performances on different metrics if you give me the time to come up with them, right? But loss is a great one. And so you can see our losses go from 3.3 to 3.6. Sorry, the other way, right? Because lower is better. So this has a huge impact, and everybody did this, and you should always do this as well. In production, this is complicated because this is 24 times as much computation, right? But this is a competition. This is not production. Other things that we did that are important to get right. So like I said, there are manuscripts. So I read one from a team that reported amazing results, but somehow they didn't win the competition. And you can make really important mistakes here. So in this case, one of the key details was in the train validation split. So this is not just photos of moles. These are photos of people's moles. And sometimes it's photos of the same mole. And different photo, same mole. And if you split those, if you take one of those and put it in your training set and one and put it in your validation set, your network has a much greater ability to essentially memorize that mole and then give a really good answer, not because it's going to generalize, not because it's going to do well on your test set. And so we saw a lot of that. It's really important to stratify your random sampling when you do this, which sometimes involves a lot of code. You probably have to press the button.
Question on the ensembling. Did you train a bunch of different networks and then ensemble those bunch of different networks? And the follow-up to that is, did you notice that some networks are better at classifying some classes? So you may have weighted that a little bit more on one network versus others?
Yeah, okay. We'll do this slightly non-linearly now, and I'll just jump to talk about, because it's on here. No, that's good. So what didn't work / matter? So I have this like high variance ensembling methods. Like, so ways you might ensemble. You might take an average. You might take a weighted average. You might also do these complicated stacking schemes, which we're not going to get into right now. But essentially, you build a model on top of your models of all their probabilities, and you use machine learning to do what you just described, to figure out that some models are better in certain cases and others in other, and learn to do it. And that didn't work in this case. I think we had diversity in our ensemble, which is what you usually want for these things. Like, you don't just want like all your networks doing exactly the same thing, because they're going to output the same answers, and they're not going to. There's no group intelligence, right? But if we can have some diversity in our ensemble, then we can start to find those opportunities, like you just described. All of our models were pre-trained ImageNet CNNs, right? That had probably at one point been published by someone who won the competition one year, right? And so if you do that, then actually you have quite little diversity. Whereas if this were a more like a non-image machine learning competition, where you might use XGBoost and you might use like GBM and you might use logistic regression, you can get like lots of really different models. And then you might want to do these more clever schemes where you stack machine learning on top of machine learning. But like a straight average of our 10 best models was actually our winning submission. How am I doing for time? I might start skipping things. 10 minutes, okay. Let me just think about the things that should really matter. That's not a big deal. Color constancy, quick interesting point. We'll like add questions at the end now, just so I make sure I get the. So this is an interesting way of taking a set of images and bringing them closer together to normalize them. Here's an example of some basic images and then what they might look at after you fix them. I'm not an expert on this, but if you're very interested, I can connect you with my colleague who is. There's different ways of constant sizing, new word, images. And so we use the shades of gray. Here's a kind of a visualization of like what our data set looked like and what the training set that was provided, and then what happens when we correct them and they all come together. This is like inconclusive as to whether or not it worked. We tried with it, we tried without it. You got like very similar performances, but diversity is very interesting. So now my ensemble has models that have seen these colorful images and models that have seen ones that aren't. And then I talked mostly about these things I wanted to touch on. Something that people do when they're fine-tuning neural networks is they only fine-tune a part of it. So they actually they hold the weights that they got from ImageNet like firm, and then at some point on, they unfreeze them. I got no benefit from doing that. Just training the whole thing was great. And even any kind of like gradual unfreezing or anything was never worth doing. Exotic approaches generally weren't worth doing. There were like a bunch of people who you could see in their manuscripts, all kinds of crazy new things, but none of them were better than doing the basic thing. I promised this earlier, so we'll just, maybe it's a little hard to read, but this is like a configuration file for some of our training augmentations. It's not that exciting, but it's worth getting right. So definitely you want to get like a lot of extra diversity. So like in training, I start with this shear, which is a bit weird, but why not? Like machine learning can be that way eventually. But like really worth thinking carefully, and we won't go through the details of it, but like when you're doing your test transforms, think about what your training transforms were. And like these numbers that I have in here, and if you looked at the presentation, you'd see them, like this 374 and these 2993, like if you do CNNs, this looks very familiar, 299, because that's like the input size for Inception, V3, and similar. But all these numbers are a bit weirder, and that's because they've been very carefully calculated to be at the ranges of the random sizes that you've trained your model on, so you cover the same distribution that it got. And these are kind of quite complex. I was going to enjoy talking about those, but so here's just like the kind of performances that we had. So our best model was actually this like average of our 10 best, like just straight average. Can't weight it or anything by their performance. It doesn't go up at all. I built this crazy meta ensemble where I use XGBoost and like GBM and a logistic regression, and then I averaged those results. And I didn't just do it once, I did it like 5 times because I was calibrating them because I wanted their probabilities to be real probabilities so that I could adjust their priors and so on and so on. And I mean, my cross-val score was lower, They had this little submission you could make. It was really noisy, but it got better, and ultimately it wasn't as good. Interesting, like we did all this crazy garbage. Our best single model scored 87.1. Although reflecting on single model, it's kind of single configuration trained in 5 folds and then averaged. So this is really like a single model score. When you do a cross-fold, you hold something out and you see how you would do. But this is actually an average of 5. So people are nodding, but other people won't. Those are the important things. So now so Bruce can tell us when we're done, and we'll go with Andrew.
Okay. My question was about finding moles or lesions from the same person. How in the world did you do that? Is there more?
There's metadata.
There's tons of metadata? Yeah, okay.
Yeah. And actually, I mean, reasonably, you could have just said, oh, photos of the same mole. But to be conservative, we just separated by person. I mean, why not, right?
I think somebody asked about the types of the model that you trained, like in Ensemble.
Yeah.
You didn't mention that.
Right, no, you're right, I didn't. So the way we approached it, we started with something smallish to iterate on, and then we gradually grew. So we started with like a ResNet 50. That was like, well, actually, I mean, I did some experiments with 18 and 34 because they run really fast. And then just gradually built out from there. And I found every step along the way we got better performance. So moving to like ResNet 101, moving to Inception v3, I got pulled out the dual path nets. I had like 68B and 92, and then Inception ResNet v2. And every time we got slightly better performance. The big dense nets as well. It took longer. And got harder to train. I didn't get the chance to talk on my slides about fine-tuning and learning rates and scheduling and how it can be really finicky. And the bigger the models, the harder it was to get right.
So is it right to say that top 10 ensemble, whatever you had average, that you had 10 different CNNs?
Yeah, so I mean, in that ensemble, I think there were probably like 2 dual PathNet 92s, like maybe 3 Inception ResNet v2s. We had a couple of more exotic participants, like these ResNet something or others. I don't remember off the top of my head. Like, so there was certainly some. It wasn't like 10 of one architecture trained in one way.
Haven't you tried to use all of them, like AlexNet, and like, just go through the list of last 6, 7 years?
Well, I mean, worth reflecting on the fact that the simple average was the best, right? But that means that stupid, diverse models aren't super valuable because because we don't have any like intelligence in our ensembling. We're not going to say, oh, like, this one's only good sometimes. So when you have that average, it's not going to contribute a lot. And so we had to be really picky. And like, I mean, I had in my cross-validation scheme, I had like all 40 models, and I knew what their cross-val score was. And it wasn't like that last one at all. The weak links really dragged the whole chain down. Matt. Oh, you're off. I mean, I've been wrong before.
Hey, yeah, okay. On one of your slides, it said industrialize experimentation.
Yeah.
Did you use a framework? Can I see your framework?
No, we wrote our own code. It wasn't a big deal. But yeah, like essentially, we could define a whole training run in a configuration file. And then we could feed that to the script that then, I mean, in Python, it's really easy to do because you can put these dictionaries that are like keyword arguments, and you can like pass them to functions. So it's really easy to take text and turn it into behaving code. And so it made experimentation really fast. It made it really easy to just queue up experiments overnight, share things with colleagues, and so on. Yeah.
You were talking about like ways to fine-tune the network and like freezing layers versus unfreezing layers. Do you think that, like, what's your intuition on why, like, basically retraining the whole set of weights worked better in this case, or do you think it works better in general?
Yeah, I mean, I think if you Googled this, I think the advice would be that if you've got a really small data set, like really, really small, then you want to freeze more and more of your network. I'm not sure that that's actually true. I think that's like a rule of thumb. I find the whole thing a little mysterious. I mean, so something I want to touch on now because I found it's very mysterious. Okay, so anyone who's reused a pre-trained network will know that like the image normalization is really important. Like like everything starts pretty much as a 0255 unsigned int, like RGB color in an image that we'd see on a screen. They almost always get turned into a 0 to 1 float. But then people do things to them. And everybody does something different. Like somebody leaves it as 0, 1. Somebody changes it from -1 to 1. Somebody takes the average of all of the R's in the data set and all the G's and all the B's, subtracts that. Some people even do it like on a per pixel basis. They end up with like this mean image. It's like crazy. That's what the cafe people did early days, I think. And it's like, and you have to get that right or else your model spits out nonsense answers. But in our experience here, if you were reusing ImageNet weights and you didn't use their normalization scheme, you just kind of use those as just to start. Like it didn't matter. And that was like, that blew my mind. Like I thought, if the model was pre-trained on -1, 1, then you'd better have your images come in at -1 to 1 when you're training. But actually, if you threw them in at 0, 1, somehow that magic pre-trained weightness, like it was good. It was, and the magic sauce wasn't diminished in any way. And so I find the whole space quite spooky and unexplained.
I was just wondering if it was related to, like if you can imagine if you were looking at ImageNet and then you were going to like a model training dog cat, something like that, then I would expect at least that basically you would do better to like not retrain the whole thing. But in this case, these images are pretty different than the ImageNet base, and maybe like allowing retraining of the earlier layers might be the thing that like does better, I guess.
Yeah, you're right. They'd say the key thing to think about is data set size and how similar is the domain, right? Robin or, at Beers.
Yeah, we're at Beers. So I have a question from the live stream, and then maybe time for one more question after that, and then we should probably take it to beer. From the live stream, maybe a little overlap with the previous question, but could you speak to your training infrastructure and training time for your models? For example, X days on a local machine or Y hours on AWS?
Okay, yeah. We had sort of 2 or 3 1080 Ti's at our disposal. I say 2 or 3 because we acquired one late in the competition. And those were basically in a single desktop computer, and we ran everything there. I would say training time for like our best single model, probably around like 4 or 5 hours for like a single crossfold. But everything we did 5 times. So that, and then like, actually when you have the really big like Inception ResNet V2s, that test time augmentation, like 24 versions of 1,000 images for 5 folds, that starts to add up as well. And so like it would take one desktop approaching a day to turn that winning solution around. But like ResNet 18s, while underperforming, can inform your design choices rapidly, and those turned around in like less than an hour, you could train 1 fold of that. And then that's going to come up and wrap this up. Oh, you can do one more question? One more question from Robin, but he doesn't have a microphone.
Robin's got one here.
How does this excellent result fit in terms of your company and what your company's doing?
Yeah, that's a good question. I think we performed better in this challenge than people expected. And I think there's a chance that we're talking about superhuman. We're certainly talking about human competitive performance here. And again, not replacing, but if we're going to help humans, we need to be pretty good, right? And so, I think it's been an important milestone for us. I mean, it's a natural ambition for our company to work on this sort of thing. I mean, especially if you have hardware and software with users, you have more data every day. Right. So every morning we should wake up with a better classifier, right? And so that's awesome, right? And so I'd say it's an important part of our direction. Yeah.
Let's thank our speaker.